going to enjoy the second fundamental.
Is it easier than the first one?
Yes.
Oh.
Yes.
But we have to do it twice.
What? Okay, so let's look at this picture right here. Nope. Nope, it's G of X.
Shouldn't it be A to X?
Nope. Oh, well, yeah. Okay. This is what we call an accumulation function. Why is this called an accumulation function?
Because it accumulates things over time.
Because we are adding up area.
It accumulates like snow.
It does.
Thanks for stealing my
Okay.
Snow accumulates like that.
Now,
It doesn't.
tomorrow we're going to work with talking about G as a function and G's derivative and G's second derivative and what it means graphically. But today we're just going to focus on the derivative of an accumulation function. Okay? What were to happen if we take the derivative of that antiderivative? That is the second fundamental theorem of calculus. I didn't even have to tell you. You figured it out. The derivative of an antiderivative is the function itself. It makes sense, right? It's logical. The derivative of an antiderivative.
With the exception of one thing. You went from f of t to f of x, which x is your ending point. So do you really just take the derivative at that ending point instead of...
Well, let's think about this. Because, like, if we do the first fundamental theorem of calculus, we're going to take f of x minus f of a, right?
Can you do an example with x squared and stuff?
Yes, I will. I will. Okay, Josh, this is for you. Okay, if we think about the first fundamental theorem of calculus, we get this, right? The antiderivative evaluated at x. Okay, well, this is going to be a number, right? So when we take the derivative of that, the derivative of a constant is 0. The derivative of the antiderivative is the function. Okay, so you're not going to see the x here. You're going to see the x here because we're plugging that in and then taking the derivative of it. Okay, so instead of having to take the antiderivative and then take the derivative of that, we just know that this is going to be the shortcut. Okay, let's take the long way around things. Okay, when we have an antiderivative, we take the antiderivative and we evaluate it, in this case, from a to x. So we have f of x minus f of a, and then we're going to take the derivative of that. Well, f of a is a constant. The derivative of a constant is 0. Excellent work. The derivative of the antiderivative gets us back to the function itself. Okay.
What's it do again? I think
T stands for it's a different variable.
So you have the x twice in
Wait, is it t
No, I don't.
time or...
Thank you. Better? Okay.
Oh, that makes sense.
That makes it go together. Thank you for pointing that out. I was looking here. Okay. So let's practice this. Don't say anything yet. Red light. Red light.
Green light.
I said red light.
Change it like that.
I just want to give people a chance to write it down before we move ahead.
What are you going to do with your study? What do you usually do?
with that a little bit. Plural. I have two of them. The derivative of this accumulation function is what, Brady?
The actual derivative would be 3t squared. Or what do you
The derivative of the antiderivative is what?
The function. Is it just t squared?
It needs to be x cubed plus 1. Okay, because it has to be in terms of x.
So I'm gonna say like,
Okay, I would like to point out, it does not matter what this constant is right here. It could be 0, it could be 3, it could be 1500, but it needs to be a constant. Okay, I'll get to an example.
is that the third? Is it fun?
There's only two fundamental theorems. Okay, because when we take the derivative of an antiderivative, we're left with the function itself. Okay. Now I know this is t cubed plus 1, but if you think about when we do this antiderivative, we're going to be plugging in x, right? And then we take the derivative with respect to that x, and so it's going to be in terms of x instead of t. Does that make sense?
You might just.
Okay, so let's talk about this. Let's actually do this the long way. Okay. So the antiderivative of t cubed plus 1 would be 1/4 t to the 4 plus t, and then we have to evaluate that from 3 to x. Right? So we have 1/4 x to the 4 plus x minus 1/4 times 81 plus 3. So will somebody just tell me what 81/4 plus 3 is? It doesn't.
Whoa.
24 seconds with.
That doesn't even make sense.
23.25.
Thank you. Okay. So now when we take the derivative of this, Carly, we get 4 times 1/4 x cubed plus 1. No, the whole point of the second fundamental theorem of calculus is to look at this and go to that.
I mean, if it's that easy, then get points taken off, you should do that.
Okay, I don't want this.
This is
I
just
don't,
like a little.
that's all I want.
Yeah, that's what I'm saying, like, if it's that easy, then why?
Oh, it gets hard.
Because when it comes to tomorrow, this is going to deal with the graph, and we need to be able to think about the graph in relation to the derivatives and minimums and maximums and decreasing and increasing values, and we got to be able to do this first. Okay?
Is this getting into those weird vector grid things? You know, things that look like something.
Aaron wants the answer. Done. I mean, this is it. This is it. Okay? Here's where you need to be careful before you just go, do, 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 do. There's my answer. Okay?
It's going to be when the text is
That's not fun. You there?
Oh,
No, we just. From sign of T to.
okay, how about you write down? So you have this to reference.
derivatives first.
Okay, so I hear people discussing, wouldn't it be sine x to the sixth? How do you feel about that? I feel like that's part of it.
6 times.
But then you have to take the chain rule. Okay, so we're going to plug x cubed into the t squared, and that's how we get x to the sixth. But then we have to do the chain rule. If we have a function inside of a function, we have to do the chain rule. So since this wasn't just x, this was x cubed, we have to multiply by the derivative. Okay, because we plug in, and then we do the chain rule.
Why wouldn't we do two chain rules?
Because we're taking the derivative, we're not taking the derivative of this.
Of just x cubed.
Yes. Okay, you're thinking that this square is bothering you with the chain rule?
Yeah.
Remember, when we have the derivative of our antiderivative, our function gets to stay the same. So whatever this is, gets to stay the same.
Okay.
And then this guy is what we use for the chain rule. Because that's what's inside of our function. Yes.
Would the derivative of the antiderivative of sine be negative sine?
Nope. The antiderivative of sine would be cosine. It would be negative cosine.
Then the derivative.
And then the derivative of negative cosine would be a positive sine.
Isn't the like the conclusion? Shouldn't the
The
phenomenon
derivative
have
of
like
negative cosine is negative.
Oh my gosh. Hey.
Right? And the derivative of negative cosine would be negative sine. So back to positive sine. Okay, anytime you're doing the second fundamental theorem of calculus, you're going forward and then backwards. Or backwards and then forwards, however you want to think of it. We're always getting back to the same place. I don't want to do that one. I want to do it.
Yeah, skipped it.
Okay? I don't know what happened to this one. My examples got all weird.
Whoa.
Just trying to get those eyes out. So now we plug in 7?
Hold on. What is the second fundamental theorem of calculus? What order do our limits of integration need to be?
Oh, so it's going to be negative.
Okay. So what we have to do is we need to rewrite this as negative integral of constant to x. Over. So then, derivative of the antiderivative, negative radical x cubed plus 1.
This is a question I have. We're automatically assuming that x is greater than 7 right here. We used to say that x isn't 2 or 3 or something smaller than 7.
Because when we integrate, we go from left to right.
Yeah,
To
so
get
you say
positive.
that x isn't on the left. So in other words, x is your beginning is the beginning and 7 is the end. I mean, I don't disagree with what you did.
Right. Hold on. But still, it doesn't matter if x is before or after 7.
Okay.
Because if x is before 7, yeah, it's still going to make it positive because you're talking about negative area, but then you're going to get to be positive anyway. Okay. Okay, change this. This is x squared. I'm going to give you 30 seconds to do this problem. Okay, that's 30 seconds. Okay, Carter. What is it?
2x cosine x squared.
You agree?
Oh, yeah.
What do you have?
Well, it's not the derivative of the antiderivative.
Oh, that's true.
Find the derivative of that.
That didn't.
Same kind of derivative of the antiderivative.
I didn't see that
That-
part.
Okay.
Are you trying to fool her?
Where did the what?
And the answer where this comes.
Whatever is here is what you have to substitute into your function. Okay, so tomorrow we'll work with the graphs a little bit more. But I want to revisit a little piece of the first fundamental theorem of calculus. Okay, so your book work, you have 6 problems that are going to take you, 6 minutes? Most of the work's going to be writing them down, or if you can write them down, I don't know. Okay, but then I have a worksheet with 7 problems. Okay, going back to the fundamental theorem of calculus, the first one. Okay, I want to go back to our differentials. Now that we know how to do and we have mastered the first fundamental theorem of calculus, I want to talk about this. Okay, so let's talk about how we did this before. What did we do? Before we knew the first fundamental theorem of calculus, what did we do?
Plug it in.
We say, okay, the derivative is 4x.
So find this actual function.
Oh, no.
Okay, so our function is the integral of 4x dx, right?
Okay, so I'll choose
So it's
Okay. Excuse me? 2x squared.
2x squared plus c.
Oh, okay.
How's that?
Then what would we do?
So c is
Plug in 0.
So then we'd say, okay, well, f of 0 is 6. So c is 6. So our function is 2x squared plus 6. And then we finally plugged in 3. Excuse me.
Is that worse?
Okay, now that we know the first fundamental theorem of calculus, we don't have to do as much work. You like that? You like less work?
Yeah. Be certain we'll do
Oh,
this.
Can you use this method? Still?
Yeah.
Yes. But what I would like you to try out for tonight's homework is this. We knew that our derivative was 4x. We knew was 6, and we wanted f of 3. So this is what we can do. We know that the integral from 0 to 3 of 4x dx should equal our function at 3 minus our function at 0. Write it down, take it in. To go from f prime to our function, we have to take the antiderivative. Well, if we are looking for places specifically, okay, we don't have to worry about what that plus c is. We can just use the fundamental theorem of calculus. Okay, does this setup make sense to everybody? Brady?
How does that find the value of f of 3? Because doesn't that f of 3 minus f of 0 only use that time like the derivative? Or what do we, like, how does that, I just want to know how that finds this the value of f minus 3. Like, integrating with that.
Okay, I will show you. Are you okay with how we set it up? Like, are you okay with this is the fundamental theorem of calculus?
The f, is it the f of b minus the f of a?
Mm-hmm. Okay, so, but we can do this without having to find c. So we know that the antiderivative is 2x squared, and we're going to evaluate it from 0 to 3. We also know that f of 0 is 6. So we have 2 times 3 squared minus 2 times 0 squared equals f of 3 minus 6. So what we can do is we can take 2 times 9, which is, and then we add 6. Why we have to know this is if we come to something where we can't integrate it by hand and we have to use our calculator, then we have to be able to do this.
Hold on.
Okay. Are there any questions?
So we can still do that if our, like, we're calling for our f b value. Or f of good.
Okay, yeah, so what we did up here is still legitimate. The only problem with that is if we don't know how to integrate it.
Like from this one on here, it's like if we were solving for, like, if we knew f of 3, we didn't know f of 0, could we still do this?
Yeah, because then you just have something minus mystery number,
Okay.
right? And so then you could, yes. Basically, you can do the first fundamental theorem of calculus if you are looking for a value and know another. Okay? If they're asking you just for f of x, well, then you have to find the plus c. If you don't, if you can just go straight to finding a value, this will work. So, I don't know if I updated this. Nope, I didn't. So, you have page 290, 81 to 91 on, and then you're going to have a differentials worksheet. On the differentials worksheet, the first few problems are just asking you to find f of x. So that'll be you actually have to go through and find the plus c. But then the last three problems I would like you to solve the way that we did it the second. Okay, so 5 through 6, I want to be like the last one that we did.